So one word that I keep using as we are having this discussion about energy are these two words, system and surroundings. And let's be a little bit more clear about what we mean by that. So when we're talking about a system, all we mean is the thing that we care about. So you can sort of imagine a box drawn around, say, a reaction that's happening. Like your chemical reaction that's happening inside your beaker. That would be our system. And then the surroundings is everything else. So everything like, the lab outside, the air around it, people that are doing the experiment around it. Everything else is, let's spell that right. Everything else composes the surroundings. So this just allows us to sort of divide our whole universe into two parts. The system, which is the thing that we're measuring or analyzing or looking at, and then the surroundings, which is literally everything else around it. And usually this will only just be the stuff right nearby it, but it effectively includes like the rest of the universe. So systems can be arbitrary size. We can think about a system of just like one atom or one molecule. We usually won't, but we could. Or it could be as large as like the whole Earth. We could consider that a system, and then the surroundings would be like the rest of the solar system or something like that. So this is sort of arbitrary size. We can go from as small as molecules and atoms to as big as the galaxies or something like that. In chemistry, we're usually going to be looking at systems around the size of a chemical reaction happening in a beaker or something like that. Now there are different ways that we can classify systems and surroundings. That will help us look at what sorts of possibilities there are. So let me grab a picture here. Give me just a second with a few examples from your textbook that I like of different types of systems and surroundings. I'll just list them here underneath my face. So we have what are known as isolated systems. These are the rarest. These are kind of hard to make. We have closed systems. These are fairly common. And then but the most common is the last one, which are open systems. And let's go ahead and look at an example. Let me just find this picture here that I'm thinking of. Not that. Not there, not there. Here we go. Let me just pull this here, and I need to just make it a little bit bigger. And we'll move this down so I don't have my stuff all over it. Okay, so we have here an example of our different types of systems. And what we're going to look at is energy and matter, and whether they can exchange between the system and the surroundings. So in an isolated system, that's our first one here. An isolated system, a sort of practical example would be like a thermos that has insulation around it to keep your coffee or your soup or whatever you have inside of it hot, or to keep something cold. This is an example of roughly an isolated system where we have no energy exchange, and no matter exchange. What that means is there's no heat that can transfer in and out. The system is rigid, so it can't push on anything around it. And it's closed. It has a lid on top of it, so no air can get in. You can't pour water inside. You can't put more soup in it until you open the lid, and then it's no longer an isolated system. And so that's our first type of system. Our second type of system is a closed system. So this is something where we do have energy exchange, but still no matter exchange. And so that's our example here of a cup of hot soup that has a lid on top of it. So heat can come in and out, and that's sort of shown here. We have heat coming in or out of the system. So the heat's leaving the soup because it just has a regular lid on it. It's going out through the sides of the bowl. It doesn't have that nice insulating layer like the thermos does. but because it has a lid on it, no soup or gas particles are coming in or out of that system. And then our most common and final is an open system, where we have matter exchange and energy exchange. So in this case, that would be like a bowl of soup that is just open on the top. So we can put stuff into it. We can add pepper or crackers or whatever. Heat's leaving it. So that bowl of soup is an open system. So these are the different types of systems we can consider. And one of the most important properties of an isolated system, this first one, is because there's no energy exchange. Sorry about that. Because there's no energy exchange, I just did the exact same thing. Because there's no energy exchange, delta E equals 0, specifically for an isolated system. You can have no change in energy because there's nowhere for it to go. Because we can't create or destroy energy, all of it stays trapped inside that isolated system. So if we're ever looking at an isolated system, we can know that it's never going to change its energy. That energy may change forms inside of the system, but it can't leave, and there's no energy from outside that can come in. So delta equals 0. If we think about open and closed systems where there is an exchange of energy, what we can also think of is that delta E total, which is equal to the energy of the system plus the energy of the surroundings, will equal 0. The reason for this, again, being the law of conservation of energy. We can't create or destroy energy, so if there's any energy that comes into the system, it has to come from the surroundings, or vice versa. If there's any energy that comes from the system, it goes into the surroundings. It doesn't disappear into nothing. And so that's another couple properties of energy that's really important. And so these are ways of looking at different types of systems. And so when we talk about a system, again, it's just whatever we're interested in the surroundings is everything around it. And we have these different isolated, closed, and open systems.